Here's a solution to problem number 13 from section 9.1. Here we're trying to find upper bounds on the error made in approximating a quantity using a Taylor polynomial. It's asking us to use the Taylor polynomial of degree 3 here to estimate a value of the cosine function. And so the function that we're estimating is cosine. They tell us that they want to have this centered at 0. And that's our a value with our polynomials. And we have done this one before, so I'm just going to write down the result. This is the thing that comes from taking the first, second, and third derivatives, evaluating them at 0, the value of a, and then getting the coefficients by dividing each of those derivative values by the corresponding factorial number. So what we get for P3 is 1 minus 1/2 x squared for cosine, and then the third derivative cosine is sine at 0 is 0. So there is actually not an x cubed term in this. These are the only two terms. So that happens with sine and cosine at 0 because every other value is 0. The cosine function, for example, will only have even degree terms, and then the sine function will only have odd degree terms. So anyway, so technically this is the cubic polynomial. The coefficient of the x cubed term is just 0. It is also the quadratic polynomial, so it's the same thing. Now, we're not actually being asked to do the approximation. If I was asked to approximate cosine of 0.49, I would plug 0.49 into this polynomial. But all they're asking for here is for us to think about what the upper bound of the error is going to be. So the theory says that the upper bound of the error at 0.49 is no more than m times, sorry, everything's shifted on me, no more than m times the distance from the approximation, so 0.49 to 0. So that, terrible time. So that difference of 0.49 to 0 to the 4th power divided by 4 factorial. So it's always one more than the degree of the polynomial. And here the m it's not, well, largest is not really the right word. M has to be it has to be greater than the 4th derivative of the function. The largest that we see the 4th derivative ever being between the center of the estimation, which is 0, and the value that I'm estimating, 0.49. So in this case, it's pretty easy just because the cosine function's 4th derivative, well, both sine and cosine are like this, but their derivatives are really easy. So the 4th derivative here is just cosine again. If you take 4 derivatives of the cosine function, you come back to the cosine function. And we know the graph of the cosine function looks like this. Cosine comes down like this. This is pi over 2, which is a little more than 1.5. So cosine is as large as 1 at 0, and then comes down right in there, so it's about 0.49. So you can see the cosine function is actually getting smaller throughout that span. So in this little, whoa, that is not what I meant to do. Well, anyway, let me just change color here. So in this area up here, we have the 4th derivative being plotted between 0 and 0.49. The largest, the farthest away from the x-axis that ever gets is at cosine of 0. So that tells us that the m can be 1. So nothing on that graph has a higher y-coordinate than 1. 1 is the largest that we see the y-coordinates. So that means that this error bound is less than or equal to 1 times 0.49 to the fourth over 4 factorial. And that's about 0.002402 something something something. And so that is the most error that I could make in using this polynomial as my estimate for cosine of 0.49. They do want the answer, so we check the D box, and they do want the answer in scientific notation. So I would write that as, for 2 decimal places, 2.4 times 10 to the minus 3, just counting over 1, 2, 3 decimal places. That's how I always taught to do it. Just count over from where the dot is to where you want it to be. So I'd have to move it 3 places, so that's 10 to the minus 3. So this will be the answer to the problem using the value of m equal 1.